Hello and welcome to my YouTube channel called Training Made Clear. Today's lesson will be Basic Electricity, Electronics, Part 2 of 3. Before we continue with the lesson, just to help you find all my other training videos, type in Training Made Clear into the YouTube search bar. For my fun channel, type in Percy's Discoveries. Basic Electronics Training Module. After completing this lesson, you should be able to identify each electronic component, understand its purpose, know how it works, recognize its terminals and polarity, read its circuit symbol, and know where it is commonly used. This module covers part 2 of 3 parts. These are all the components we will be covering in this course. We've already done part 1. If you haven't seen the video, please watch video number 1. Part 2 is the blue part, which we are doing today, from 7 to 12. And 13 to 18 is part 3, which we'll be covering next. These are all the components that you will be doing. Today's lesson will be the blue part. We have done part 1, all the yellow ones. So today we will be tackling Triacs, Diacs, Thyristors, LEDs, photocell, and coil, part 2. Part 3 is the green ones, and that we will be doing in the next video. So please keep a lookout for that video. These are what all the components look like. We've already done the yellow area, so watch video 1 for that one. From 7 to 12, those are the ones we will be doing today, and the next time will be all the green ones. So Triacs, that's what one looks like. There's the physical construction, the circuit symbol, so that you know what that looks like. Right, Triacs. A triac is a triad for alternating current. Description: a triac is an electronic switch designed to control AC alternating current. It can conduct electricity in both directions. The function: controls AC power. Identification: usually supplied in a black T0220 package with 3 legs. Common types: BT136, BT137, BTA16. Uses: light dimmers, fan speed controllers, heater controllers, and motor speed control. Polarity: no positive or negative polarity because AC changes direction. Composition: made from several layers of silicon semiconductor materials. Terminals: 3 terminals, MT1, MT2, and gate. And there is the symbol. A triac is an abbreviation for triode AC switch, which consists of 2 anti-reverse connected thyristors packaged together, sharing a common gate. Unlike unidirectional thyristors that only conduct DC in a single direction, triacs are designed for AC control. It features 3 terminals, MT1, MT2, and G, where G is the gate terminal used to trigger conduction between MT1 and MT2 bidirectionally. How it works: a small pulse applied to the gate turns the triac on. Once on, it continues conducting until the AC current falls to 0. These are the different triacs, what they can look like, their composition, and their symbols. There is the triac symbol and what it looks like. There is a circuit diagram using a triac. Once a trigger current is applied to the G terminal, the triac will remain in the on state. So how do you turn it off? There are two methods. The first method is to disconnect the main power supply to the MT1 and MT2 terminals. The second method is to remove the gate trigger signal, and the triac will automatically turn off when the next load current naturally crosses zero. This method of turning off by utilizing the zero crossing characteristic of the AC current is the basis for AC phase control, such as dimming and speed regulation, and the operation of solid-state relays. A triac can control the speed of some AC motors, but it works very differently from a variable frequency drive, VFD. The important difference is VFD controls motor speed by changing the frequency of the AC supply. Triac controls motor speed by changing the voltage supplied to the motor. A triac does not change the frequency. How a triac controls motor speed. Think of the AC electricity as a smooth wave that rises and falls 50 to 60 times every second. Normally, the entire wave reaches the motor. Gate pulse triggers at 75% of the AC wave. Therefore, the motor receives 75% of the voltage. When a triac is used, the triac acts like a very fast electronic switch. Instead of turning on at the beginning of every AC wave, it waits a short time before switching on. For example, delayed switching. The first part of each wave is removed. The motor therefore receives less electrical power. Less power means less torque, lower speed for suitable motors. Where triac speed control is used. A triac works well with universal brush motors such as those found in electric drills, routers, vacuum cleaners, food mixers, sewing machines, some small fans. It is also widely used in light dimmers. Why triacs are not used for large induction motors? Most industrial motors are induction motors. If a triac simply reduces the voltage, the motor loses torque, it may overheat, speed changes very little under load, and efficiency decreases. A variable frequency drive, VFD, solves this by changing the frequency, allowing the motor to run slower while still producing useful torque. Simple analogy. Imagine filling a bucket with water. Tap fully open, the bucket fills quickly. Tap half open, the bucket fills more slowly. The triac is like turning the tap on later during each filling cycle, so less water reaches the bucket. Right, here we have a nice diagram showing the blue high speed, the green medium speed, and the yellow low speed. If you look at the bottom pulse, which is the input wave, we pulse with those red arrows. If we pulse, say the first arrow, you can see it's pulsing, and the output wave only starts sending output at about 75%, and the same on the negative wave. So in the diagram above, we see that the triac gate switches at 75% and the motor runs at high speed. When we see the medium green speed, this happens when the triac gate switches at 50%. Low speed happens when the triac switches at 25%. Diacs. That is what a diac looks like. Description. A diac is a two-terminal triggering device. Function. Provides a trigger pulse to switch on a triac. Identification. Very small cylindrical or bead-shaped component. Common type is DB3. Uses. Lamp dimmers. Fan controllers. Motor speed controls. Polarity. No polarity. Can conduct in either direction. Terminals. Only 2 terminals. Composition. Silicon semiconductor. Symbol. There's the symbol and there's another type of symbol. There we have the Diacs symbol and the structure. Diac is an acronym that stands for diode for alternating current. It is a 2-terminal bidirectional switch that conducts in both directions when the applied voltage exceeds its breakover voltage. It cannot amplify or offer controlled switching. It belongs to the family of thyristors, but it is an uncontrolled switch because it does not have a control or gate terminal. Its name implies that it is a diode and can conduct AC in both directions. It is mainly used for triggering other devices such as Triac due to its symmetrical switching characteristics. Diac is a 5-layer device from the combination of 2 antiparallel SCR without the gate terminals. It has only 2 terminals, MT1 and MT2. It has symmetrical structure from both terminals having equal width of the regions as well as its doping percentage. Working of Diac. The Diac can conduct current in both directions unless the applied voltage falls below the breakover voltage. Suppose the applied voltage at MT1 is positive with respect to MT2. The junctions at the ends becomes forward biased and the middle junction becomes reverse biased. At this moment, the applied voltage V is smaller than VBO breakover voltage, so the middle junction remains reverse biased and does not allow current to flow. The device remains in an off state. The working of a Diac. In the next slide, you will see a picture showing how the Diac D1 allows the positive AC wave to switch the gate of the Triac U1, then switch it again as the negative wave begins. Each switching time is determined by the position of the potentiometer RP2 and the capacitor C1 discharging when the threshold is reached. Here is the diagram. You can see there are 2 directions of current flow, an orange or yellow line and a green line. Note 1, which is in yellow. We have a small current flowing in yellow, charging up capacitor C1, with the Triac U1 is in the off position, and the output is off. The output you can see is off with that red line on the output wave. On the positive AC wave, when the value of the capacitor reaches the threshold value of the Diac D1, this will allow the current to flow towards the gate of the Triac, and that's what activates it. See the pink comments on the picture. Looking at the output waveform, we see that the pink output result. Note 2. When the AC input wave reaches 0, about to change polarity, going to the green AC wave, the green dotted line, the Triac switches off because the Diac D1 is under the threshold voltage. And C1 in green starts charging up again, note 3, reaching the threshold value of the negative wave, and the Triac switches on, producing the negative green output, where you can see there on the output wave there by note 4. Note 4 in green. When the AC input wave reaches 0, about to change polarity, the green dotted line, the Triac switches off and C1 starts charging up again. And we repeat note 1 again in yellow. So depending where we set the potentiometer RP2, we will affect where the output wave form will turn on. because this makes the charging process of capacitor C1 faster or slower, changing the amount of output wave, hence increasing or decreasing motor speed. So this is how the Triac AC dimmer circuit can dim AC power for motors and more. And we can see how the Diac D1 allows the current to flow in both directions, switching the Triac U1. Thyristors SCR. There's a picture of one on the right. Description. SCR means silicon controlled rectifier. It acts like an electronic switch. Function. Controls DC or rectified AC power. Identification. Looks similar to a transistor. 3 leads. Common types: C106, BT151. Uses: battery chargers, motor controls, power supplies, welding machines, polarity. There you can see the anode, the gate, and the cathode, the construction. Polarity is yes. Current only flows from anode to cathode. Terminals: anode A, cathode K, and gate G. Composition, you can see on the drawing in the middle, that's the composition. 4 layers of silicon, PN, PN. This is the symbol. How it works. A small gate current switches it on. It remains on until the current falls below its holding current. Transistors are amazingly versatile, but that doesn't mean that they can do everything. They're not very useful when it comes to handling much bigger currents. Another drawback is that they turn off altogether as soon as the switching current is removed, which means they're not so useful in devices such as alarms, where you want a circuit to trigger and stay on indefinitely. For those sorts of jobs, we can turn to somewhat similar electronic component called the thyristor, which has things in common with diodes, resistors, and transistors. Thyristors are reasonably easy to understand, though most of the explanations you'll find online are unnecessarily complex and often confusing beyond belief. So that's our starting point. Let's see if we can take a clear and simple look at what thyristors are, how they work, and what kinds of things we can use them for. What are thyristors? First, let's nail some terminology. Some people use the term silicon controlled rectifier, SCR, interchangeably with thyristor. There are various other kinds of thyristors too, including ones called Diacs and Triacs, which are designed to work with alternating current. Keeping things simple, we'll just talk about thyristors in the most general terms and assume SCRs are exactly the same thing. So what is a thyristor? It is an electronic component with 3 leads called the anode positive terminal, cathode negative terminal, and the gate. In a thyristor, the gate controls the current that flows between the anode and the cathode. It's worth noting that you can get thyristors with 2 or 4 leads, as well as 3 lead ones, but keeping things simple, so we'll just talk about the most common variety. In a thyristor, a small current at the gate triggers a much larger current between the anode and the cathode. But even if we then remove the gate current, the larger current keeps on flowing from the anode to the cathode. In other words, the thyristor stays latched on and remains in that state until the circuit is reset. Where a transistor generally deals with tiny electronic currents, milliamps, a thyristor can handle real electric power. Current several hundred volts and 5 to 10 amps is typical. We can use transistors in such things as factory power switches, speed controls for electric motors, household dimmer switches, car ignition switches, surge protectors, and thermostats. Switching time is practically instantaneous, measured in microseconds, and that useful feature, coupled with the lack of moving parts and high reliability, is why thyristors are often used as electronic solid-state versions of relays, electromagnetic switches. A thyristor is like two diodes. Recall that a diode is two layers of semiconductor, P-type and N-type, sandwiched together to produce a junction where interesting things happen. According to how you wire up a diode, current will either flow through it or not, making it the electronic equivalent of a one-way street. With a positive connection to the P-type blue and a negative connection to the N-type red, a diode is forward biased, so electrons, black dots, and holes, white dots, move happily across the junction and a normal current flows. In the opposite configuration, with a positive connection to the N-type and a negative to the P-type, a diode is reverse biased. The junction becomes a huge chasm that the electrons and the holes cannot cross and no current flows. In a transistor, we have three layers of semiconductor arranged alternatively either PNP or NPN, giving it two junctions where interesting things can happen. A FET is slightly different with extra layers of metal oxide, but still essentially an NPN or PNP sandwich. A thyristor is simply the next step in the sequence 4 layers of semiconductor, again arranged alternatively to give us PNPN or NPNP if you swap it around, with 3 junctions in between them. The anode connects to the outer P layer, the cathode to the outer N layer, and the gate to the internal P layer like this. You can see that this resembles two junction diodes connected in series but with the extra gate connection at the bottom. Just like a diode, a thyristor is a rectifier. It conducts only in one direction. You can't make a thyristor simply by wiring two diodes in series. The extra gate connection means there's more to it than just that. A thyristor is like two transistors. What's less obvious is that the 4 layers work like two transistors, an NPN and a PNP, that are connected together so that the output from one forms the input to the other. The gate serves as a kind of starter motor to activate them. The 3 states of a thyristor: number 1, forward blocking, off state. Normally, with no current flowing into the gate, a thyristor is switched off. No current can flow from the anode to the cathode. Why? Think of the thyristor as two diodes joined together. The upper diode and the lower diode are both forward biased. However, that means the junction in the center is reverse biased, so there's no way for the current to get all the way from the top to the bottom. This state is called forward blocking. Although it's similar to forward bias, in a conventional diode no current flows. Reverse blocking, off state. Suppose we reverse the anode and cathode connections. Now you can probably see that both the upper and lower diodes are reverse biased. So still no current flows through the thyristor. This is called reverse blocking, and it's analogous to reverse bias in a simple diode. Forward conducting on state. The third state is the really interesting one. We need the anode to be positive and the cathode negative. Then, when a current flows into the gate, it switches on the lower transistor, which switches on the upper one, which switches on the lower one, and so on. Each transistor activates the other. We can think of this as a kind of internal positive feedback in which the two transistors keep feeding current to each other until both of them are fully activated, at which point current can flow through them both from anode to the cathode. This state is called forward conducting, and it's how a thyristor latches or stays permanently on. Once a thyristor is latched on like this, you can't turn it off simply by removing the current to the gate. At this point, the gate current is irrelevant, and you have to interrupt the main current flowing through from the anode to the cathode, often by switching off the power to the entire circuit. This slide will explain how it works. How a thyristor latches on. You'll notice I've redrawn the thyristor so it looks like two transistors, a PNP at the top and an NPN beneath it, connected together with the anode and cathode and gate making three external connections. Each transistor acts as the input to the other. Number one, with no current flowing into the gate, the thyristor is switched off and no current flows between the anode and the cathode. Number two, you can see we have now power at the gate. When a current flows into the gate, it effectively flows into the base input of the lower NPN transistor, turning it on. Number three, now you can see with the gate on, the transistor is flowing. Once the lower transistor is switched on, current can flow through it, activating the base input of the upper NPN transistor, turning that on as well. Number four, once both transistors are turned on completely saturated, current can flow all the way through both of them, through the entire thyristor from the anode to the cathode. Number five, now you can see the gate is switched off. Since the two transistors keep one another switched on, the thyristor stays on, latches, even if the gate current is removed. Number 10. LED light emitting diode. Description. A diode that produces light. Function. Converts electricity into light. Identification. Clear or colored plastic body. Long leg is positive, short leg is negative, flat edge is negative. The uses: indicators, displays, flashlights, TV remote indicators, traffic lights. Polarity, yes, positive and negative. Must be connected correctly. Terminals, anode positive, cathode negative. Composition, semiconductor material that emits light. Here you can see the symbol, the arrows point outward. How it works: current flows through the junction, energy is released as light. Light emitting diodes, commonly called LEDs, are real unsung heroes in the electronics world. They do many different jobs in all kinds of devices. They form numbers on digital clocks, transmit information from remote controls, light up watches, and tell you whether your appliances are turned on. Collected together, they can form images on a jumbo television screen or illuminate a traffic light. Basically, LEDs are just tiny little bulbs that fit easily into an electrical circuit, but unlike incandescent bulbs, they don't have filaments that burn out. They use less electricity and they don't get especially hot. They're illuminated solely by the movement of electrons in a semiconductor material, and they last just as long as the standard transistor. The lifespan of an LED surpasses the short lifespan of an incandescent bulb by thousands of hours. Because of these advantages, tiny LEDs are one of the most popular technologies used to light LCD TVs. LEDs have several advantages over conventional incandescent lamps, but their main advantage is efficiency. In an incandescent bulb, the light production process involves generating a lot of heat. The filament must be warm to illuminate. This energy is completely wasted unless you're using the lamp as a heater, because a huge portion of the available electricity isn't going towards producing visible light. LEDs generate very little heat, relatively speaking. A much higher percentage of the electrical energy is going directly to generating light, which cuts down the electricity demands considerably. Per watt, LEDs output more lumens or quantities of visible light than regular incandescent bulbs. Light-emitting diodes have a higher luminous efficiency. That means how efficiently electricity is converted into visible light. Than incandescents. A 60-watt incandescent bulb can generate between 750 to 900 lumens, but you can get the same output from an LED bulb using only 6 to 8 watts. And that same LED bulb can last 25,000 hours, but the 60-watt light incandescent is only likely to light up for about 1,200 hours. In other words, one LED bulb can last as long as 21 60-watt incandescent bulbs burning consecutively. LEDs, light-emitting diodes that are just as bright as bulbs, last virtually forever and use hardly any energy at all. An LED is a special type of diode, a type of electronic component that allows electricity to flow through in only one direction. Diodes have been around for many decades, but LEDs are more recent development. Let's take a closer look at how they work. LEDs are simply diodes that are designed to give off light. When a diode is forward biased so that the electrons and holes are zipping back and forth across the junction, they consistently combining and wiping one another out. Sooner or later, after an electron moves from the N-type to the P-type silicon, it will combine with a hole and disappear. That makes the atom complete and more stable and gives off a little burst of energy, a kind of sigh of relief, in the form of a tiny packet or photon of light. I love this description, the sigh of relief. When the free electron finds a hole, the atom becomes satisfied and a burst of energy is shown by a photon of light. It's like people, when they find their soulmate, they are happy and brighter. This diagram summarizes what happens. First, the N-type silicon red has an extra electron black. Second, P-type silicon blue has extra holes, white. Thirdly, battery connected across the p-n junction makes the diode forward biased, pushing electrons from the N-type to the P-type and pushing holes in the opposite direction. Electrons and holes cross the junction and combine. Photons, particles of light, are given off as the electrons and holes recombine. There is a table of LEDs, colors and materials. And you can see I've highlighted blue, green and red. And you can see the wavelengths for those different colors. And then you can also see the voltages and the materials that are used. So types of LEDs. LEDs are specifically designed so that they make light of a certain wavelength, and they're built into rounded plastic bulbs to make this light brighter and more concentrated. Red LEDs produce light with a wavelength of about 630 to 660 nanometers, which happens to look red when we see it. Blue LEDs produce light with a shorter wavelength of about 430 to 500 nanometers, which we see as blue. You can also get LEDs that make invisible infrared light, which is useful in things like magic eye beams. that trigger photoelectric cells in things like optical smoke detectors and intruder alarms. Semiconductor lasers work in a similar way to LEDs but make purer and more precise beams of light. Here you can see the light spectrum, all the different colors that make up our light spectrum. Here you can see a wavelength and the different colors. In the wavelengths of nanometers, the red wavelength is 700 to 635 nanometers. Orange is 635 to 590 nanometers. Yellow is 590 to 560 nanometers. Green is 560 to 520 nanometers. Cyan is 520 to 490 nanometers. Blue is 490 to 450 nanometers. Violet is 450 to 400 nanometers. LEDs achieve a massive spectrum of colors through two main methods: semiconductor chemistry for single color emitting diodes and light mixing for color changing bulbs. Different semiconductor materials and impurities dictate the exact wavelengths emitted when current passes through the diode. Single color LEDs. The base color depends on the core materials used. For example, using aluminium gallium arsenide yields red light, while indium gallium nitrate creates blue light. The specific combination defines the exact energy gap, which translates to a precise wavelength and visual color. Color changing RGB LEDs. Color changing strips and smart bulbs contain 3 tiny microchips inside a single housing, one red, one green, and one blue. By finely adjusting the brightness of each of these 3 channels using an additive color model, the system mixes them to create millions of different hues. Creating white light. White light is produced by blending all 3 colors simultaneously or by coating a blue LED with a specialized phosphor that shifts a portion of the blue light into yellow, combining it to make a standard white light. Photocell, light dependent resistor, LDR. A photocell or photoresistor is a light sensitive sensor that detects the presence and intensity of light. It automatically alters its electrical resistance based on how much light strikes its surface, typically having lower resistance in bright light and higher resistance in the dark, which is used to trigger automatic electrical switches or dimmers. The description: a resistor whose resistance changes with light. Function: detects light levels. Identification: round disc with zigzag pattern. 2 leads. Uses: automatic lights, street lights, burglar alarms, solar lighting. Polarity: no polarity. Terminals: 2 terminals. Composition: cadmium sulfide CDS or similar photosensitive material. The symbol has 2 arrows pointing towards the resistor. How it works: bright light, resistance becomes low; darkness, resistance becomes high. What is a photocell and how does it work? A photocell is a device that can automatically turn an LED light on or off based on the amount of ambient light available. It is particularly useful for outdoor area lighting. To function properly, they need to be placed in an exposed area where they can receive sufficient light. Photocells, also known as photocontrols, come in various shapes and sizes and can be integrated into a luminaire or added as an accessory, depending on the specific light fixture. Can a photocell be bypassed? In some cases, it is possible to bypass a photocell when needed. Bypassing the photocell allows the luminaire to remain continuously on or be controlled by an existing switch or timer. The method of bypassing depends on the type of photocell and how it is installed in the fixture. Common bypass options include using a short-in cap, a slide or dip switch, or disconnecting the wiring of the photocell. The short-in cap. In many commercial applications such as parking lots and area lighting, photocells are externally mounted using a twist lock socket or adapter. By replacing the photocell with a short-in cap, the circuit in the LED light fixture is closed, keeping the light in an always onward state. Dip switch or slide switch. Dip switches and standard slide switches are commonly found in canopy lights and dusk to dawn barn lights. They allow you to toggle the photosensor on or off according to your needs without the need for rewiring or replacing any components. There are essentially three types of photoelectric cells: photoemissive cell, photovoltaic cell, and photoconductive cell. There's a construction of a photoemissive cell. A photoemissive cell, often called a phototube, is a vacuum tube containing a light-sensitive cathode and anode. When the light strikes the cathode, it releases electrons via photoelectric effect, which are then attracted to the positive anode to generate an electric current proportional to the light's intensity. How it works. Construction. The cell consists of a glass quartz bulb housing two main electrodes under a vacuum or low-pressure inert gas. Cathode. The cathode is typically a curved metal plate coated with a photoemissive material such as cesium or antimony. Anode. The anode is slender wire or rod positioned at the center of the cathode's curvature. Operation. When photons of light hit the cathode's surface, they eject electrons. An external battery applies a positive potential to the anode, pulling these electrons across the tube to establish a measurable current. Types of photoemissive cells. Vacuum phototubes. The air is completely removed from the glass envelope. They offer very fast response times, but generate smaller electrical currents. Gas-filled phototubes contains an inert gas at low pressure. Electrons emitted by the cathode collide with gas atoms, causing ionization that amplifies the total current produced. Photomultiplier tubes, PMTs. Highly sensitive variations that contain additional electrodes called dinodes. They multiply the number of electrons through a cascading effect, making them capable of detecting incredibly faint light signals. Common applications. Photoemissive cells have historically played massive roles in automation and optical technology, though many have been replaced by solid-state photodetectors in consumer electronics. Uses include motion pictures, reading the optical sound tracks on traditional film strips, safety systems, triggering burglar alarms and fire alarms when a light beam is interrupted, automation, controlling automatic doors, illumination meters and street lighting, instrumentation, spectrophotometers, night vision devices, and medical radiation detectors. The photovoltaic cell. A photovoltaic PV cell is an electronic device that converts sunlight directly into electricity using the photovoltaic effect. When photons hit the cell's semiconductor material, They dislodge electrons, generating a direct current, DC, that can be harnessed to power homes, businesses, and electrical grids. How it works. Absorption. Sunlight photons strikes the semiconductor material, most commonly silicon. Excitation. The absorbed energy frees electrons from their atoms. Current flow. An internal electric field forces these free electrons to flow in a specific direction, creating an electrical current. Collection. Metal conductive plates and grids on the cell gather this electricity and route it out to an external circuit. From cell to system. Individual photovoltaic cells produce a small amount of electricity, often around 0.5 volts, to create usable power. They are combined into protective weather-resistant modules, solar panels, which can then be wired together into massive arrays. Because the PV cells produce DC electricity, residential and commercial systems require a solar inverter to invert this into usable alternating current, AC power. The photovoltaic effect and its principle, and there you can see below it a field full of solar panels. Common materials. Crystalline silicon, the undisputed industry leader, making up about 95% of the commercial market. This includes both monocrystalline, high-efficiency, single crystal structure, and polycrystalline, cost-effective, multiple crystals variants. Thin film, materials like cadmium telluride, CDTE, or CIGS, copper, indium, gallium selenide. They are flexible and lightweight, but generally less effective than silicon. Perovskites, a rapidly emerging, highly efficient printed material that researchers are working on to scale commercial durability. The photoconductive cell. A photoconductive cell, also known as a photoresistor or light-dependent resistor, LDR, is a passive semiconductor device whose electrical resistance decreases as the intensity of incident light increases. When it's dark, its resistance can exceed 100 kiloohms, which drops to just a few hundred ohms when illuminated. How it works. The device relies on the photoconductive effect. The cell's photosensitive material, typically cadmium sulfide, CDS, or cadmium selenide, CDSE, is coated on a ceramic substance in an interdigitized zigzag pattern to maximize surface area and resistance. In the dark, valence electrons are tightly bound, resulting in high resistance. When exposed to light, incoming photons transfer their energy to the bound electrons, freeing them to become charge carriers. This breaking of covalent bonds generates electron holes or pairs, causing the material's conductivity to increase and its resistance to drop. Common applications. Because of their responsiveness and compact size, photoconductive cells are widely used in a variety of electronic and safety systems. Automatic light control, frequently used to turn on street lights at dusk and off at dawn, or to adjust camera iris controls. Safety devices, Used in smoke detectors where smoke interrupts the light path to the cell, triggering an alarm. Electronic switching, employed in a relay, control circuits, and light-sensitive alarms to switch transistors on and off depending on ambient light. The most common type of photoconductive cell, often called the light-dependent resistor, LDR, or CAD cells, is made from cadmium sulfide, CDS. It is widely used because of its spectral response closely matches the human eye, making it highly effective for visible light sensors. Cadmium selenide, CDSE, is another frequently used material known for faster response times but higher temperature sensitivity. You can typically find these sensors in consumer electronics, street lights, camera lights, meters, and security devices. Number 12, our final component, quill, inductor. There's a picture of a quill. What is a quill in electronics? A quill in electronics is a length of conductive wire wound into a spiral or helix. Its primary purpose is to interact with magnetic fields. It generates a magnetic field when electric current flows through it, or conversely, it generates a voltage when exposed to a change in magnetic field. Key electronic roles. Coils, frequently referred to as inductors in circuit diagrams, are passive components designed by the letter L. Their operation and applications rely on a property known as inductance, measured in henries, H. Filtering and smoothing. Because of self-induction, coils oppose rapid changes in electrical current in power supplies. They are used as chokes to block high-frequency AC noise while allowing smooth DC to pass. Energy storage. Coils store energy temporarily in a magnetic field. This property is crucial in switched mode power supplies, SMPS, and voltage converters. Transformers. When two or more coils are placed close together, the magnetic field of one induces a voltage in the other. This allows transformers to step AC voltages up or down safely. Electromagnets and motors. By forcing current through a coil, it functions as a strong magnet. This mechanism drives relays, solenoids, and electric motors. Resonant circuits. Coils combined with capacitors form resonant or tuned circuits that can filter specific frequencies, a fundamental concept in radio tuners and wireless communication. Construction. The behavior and strength of a quill depends entirely on its physical construction. Turns. The number of loops in the wire, more turns generally means higher inductance. Core material. Coils can be air core, hollow inside, or wound around a magnetic core like iron or ferrite. A magnetic core greatly concentrates the magnetic field and boosts induction. Shapes. Coils can be wound as standard solenoids, flat planular spirals, or tutorial donut shapes, each chosen to minimize electromagnetic interference, EMI, or fit into specific circuit boards. Coil inductor. An electronic coil is also commonly called an inductor. It is a passive electrical component that stores energy in a magnetic field when an electric current passes through it. It consists of insulated wire wrapped into a spiral or helix around the core, like iron or ferrite. Its defining characteristic is inductance, measured in henries, H, which opposes sudden changes in electric current. Description: a coil of insulated wire. Function: stores energy in a magnetic field. Identification: looks like copper wire wound into loops. Can have air core, an iron core, or a ferrite core. There's our inductor, and there's also the symbol for it. Uses: filters, transformers, radios, power supplies, motors. Polarity, normally no polarity. Some specialized inductors may have marked terminals, but standard coils do not. Terminals, 2 terminals. Composition, copper wire wound around a core. There's the inductor symbol, or it can look like that. How it works: current flowing through the coil creates a magnetic field. When current changes, the magnetic field opposes the change, helping smooth current and store energy temporarily. Here is a summary table of components and their functions. The component and the main function. A triac controls AC power. The diac triggers a triac. A thyristor SCR controlled power switch. LED produces light. Photocell LDR detects light. Coil inductor stores energy in a magnetic field. Here's a key polarity summary and a quick memory guide. What has polarity and what has no polarity. Thyristor and LED both have polarity. No polarity is triacs, diacs, photocells LDR, and standard coils or inductor. There is a key polarity summary where it has the component, what has polarity, and a simple explanation. A triac has no polarity. A triac conducts current in both directions. Main terminals MT1 and MT2 are not permanently positive or negative because the AC supply changes polarity 50 to 60 times per second. A diac has no polarity. A diac is a bidirectional trigger device. It conducts equally in either direction once its breakover voltage is reached. A thyristor, it has polarity. An SCR is polarized. The anode A must be positive with respect to the cathode K for it to switch on when the gate G is triggered. LED light emitting diode. It has polarity. LED only works when connected correctly. The anode A positive connects to positive and the cathode negative connects to negative. Reversing the polarity prevents it from lighting, and excessive reverse voltage can damage it. A photocell LDR has no polarity. A light-dependent resistor, LDR, is simply a resistor whose resistance changes with light. It can be connected either way around. Note, a photodiode or phototransistor does have polarity. A coil inductor, normally no. A standard inductor has no polarity and can be connected in either direction. However, coils with center taps or transformer windings use dot markings to indicate winding polarity or phase when multiple windings interact. These are all the components that you have now learned more about. Let's test your memory. Stick around and do the multi-choice test.